So let's consider the magnetic force on a current carrying wire. After all, a current is just moving charges, so those charges in motion should experience a force in a magnetic field. Let's see what that force would be equal to. So let's calculate the magnetic force on the wire by considering the current as consisting of a collection of charges that are all moving with the same velocity, which we have called the drift velocity. In that case, then, the force on each charge would be Q v drift cross into B. So now it becomes a matter of calculating how many charges we're talking about. Let us say we have a length of wire L, and we would know then that the number of charges in that length of wire would be N times the volume of that length of wire, where N is the number of charges per volume. But the volume of that length of wire would be the cross-sectional area of the wire times the length. So therefore, the number of charges in that volume would be N times A times L. And that means the force on that length of wire would be Q v drift cross into B times NAL. Now you probably have already seen where this is going, because we have seen our number of charges per volume before. This is our formula we just derived. But the current is proportional to that drift velocity. In fact, we found out that the current is equal to the number of charges per unit volume times the charge of each charge times the drift velocity times A. And that all becomes the current. Well, we can replace the terms in that formula for the current in the formula for the force, and we find out that the force on a length L of a wire with a current I is equal to IL cross B, where the direction of the current is considered to be the direction of the wire. If the length of the short segment, then we have to integrate over a segment of wire. We would say that the little bit of the force is equal to I times a little bit of the length crossed into B. Therefore, the overall force would be the integral of I dl cross B. Let's see this formula in action on a very important example. Let us say we have a loop of wire in which a current of I is flowing. Now, just for simplicity, for right now, we're going to say that the loop is rectangular, although in the result we're going to derive, it doesn't actually have to be rectangular. So the dimensions of my rectangular loop are going to be A times B, where A is the length of the loop and B is its width. And let us say that a magnetic field is oriented parallel to the loop. So it's going to be going this way. Answer these questions then. What is the force on each side of the loop? And then what would be the net force on my loop? And what would be the net torque on my loop? The formula that we just derived, if you want to write it down while you're doing this, is the force on each segment is equal to IL cross B. Okay, so if our magnetic field is going the way I've pictured it here, the force on side 1 is going to be IAB, because the current is going perpendicular to the magnetic field, and its ILB is the magnitude of the force, and so it's IAB on that side. On one of the shorter sides, since the shorter sides are parallel to the direction of the magnetic field, the force is going to be 0. On the other side, side 3, let's call it, the force is going to be IAB again. And let's consider the direction of those two forces. So on the one side, to the right of our diagram here, if your current is going up in the direction that the arrow is pointing for I, and your magnetic field is going kind of across the rectangle, that's your B, then IL cross B would give you a force that points up. On the other side, you get the exact opposite. If now your current is going back towards the left side of the paper and your magnetic field is still going across, then your thumb would be pointing down in your right hand, and so the force would be pointing down. And on the fourth side, your magnetic force is going to be 0. So therefore, the net force on your current loop is going to be IAB minus IAB. In other words, it's going to be 0. There is not going to be a net force on a current loop in a uniform magnetic field. But what about the torque on a current loop? Let's take a look and calculate the torque about this axis here, as I have drawn it in with a dotted line. Now, the torque on the side 1 would be the force on side 1 times the distance that side 1 is from the axis of rotation. So that would be IAB, that's the force, times little b over 2, that's the distance it is. And we can see that the torque that it would exert, since that force is going up, would tend to rotate this current loop counterclockwise. Since there's no force on side 2, there is no torque exerted there. There is the same amount of torque exerted on side 3 as there is on side 1, because it's the same amount of force and the same distance to the axis of rotation. But now this torque is also going counterclockwise because the force over here pointed down. And on side 4, there was, again, no torque. So the total amount of torque that we have is IAB times little b over 2 plus IAB times little b over 2, which gives me I times big B times A times B. And you remember your geometry well enough from grade school to know that the length times the width of a rectangle is its area. So indeed, the torque exerted on a current loop in a uniform magnetic field is going to be equal to I times B times the area of the current loop. And although we've derived it for a rectangular loop, this is a general formula. Now, we chose a very special orientation for our current loop and our magnetic field to get that previous result. Clearly, the amount of torque you get is going to depend on how the magnetic field is oriented relative to the current loop. To see how we should state that formula, we're going to define a unit vector for a current loop as n, little n. Little n points perpendicular to my current loop, but that's going to give me the direction of the loop. This is kind of like how we defined a surface area vector when we were doing Gauss's law. So n is perpendicular to the plane of the loop, and it points in the direction given by the right-hand rule. That is to say, if you let the fingers of your right hand curl in the direction that the current is flowing in your loop, your thumb will point in the direction that n points. Now, you can take a little bit of time to convince yourself of the following fact, but F makes the same angle with the vector going from F to the axis as N makes with the magnetic field B, the F being the force that is produced by that magnetic field. So therefore, we can write the formula for the torque on a current loop is I times A, the area of the loop, times the unit vector n crossed into B. Remember, n is just a vector to give us the direction of the current loop faces. If there's more than one loop, then you need to add a number of loops that you have. In this case, I've used uppercase N. This doesn't stand for the number of charges per unit volume right now. It just stands for how many loops I have that are going to be experiencing torque in this magnetic field. So the general formula for the torque experienced by a current carrying loop or loops in a magnetic field is the number of loops times the current of each loop times the area of the loop crossed into the magnetic field. We can take all of the quantities that are descriptive of the loop and don't depend on the magnetic field. We can define a quantity that is given by all of those. So if you have a current loop, we are going to define the magnetic dipole moment, mu, of that current loop is going to be defined as N, where N is the number of loops, and I is the current flowing through each of our current loops, and A is the area of our current loop, and the unit vector N gives the direction that the area is pointing. If that's the case, then the torque is going to be equal to mu cross B.